Alright, making a video, I think. Uh, yeah. So, my back is just, it's a week now. And, it's been going kind of slow, getting better, so I kind of pushed it today, trying force some exercises and things, but I think I made it worse again. It's really irritating. But, it could be worse and whatever, blah, blah, blah. Anyway, the acorn guy. Gary, sorry for my last comment, was a bit weird. What I meant by it is there really doesn't exist a person on YouTube with your uniqueness, take, and ideas. Okay. It does seem strange though, doesn't it? I mean, it's a big world full of lots and lots of people, and you do sort of think, yeah, there should be something that's pretty samey. I mean, I shouldn't be 1 in a million or something. But yeah, it's hard to find anything like me anywhere. You provide insight into things that never really really got bothered with or questioned. Okay. Yeah, and why is that though? So that's the problem. I don't it should be something, it shouldn't require a me. I shouldn't have to show up and explain to scientists how to be scientists, that they aren't supposed to be jumping to conclusions and, doing all this, I don't even know how to describe it. But it's like I was saying, you can read Wikipedia pages and there's just no distinction between the stuff that actually has evidence, like they found some bones, and the stuff where they're just conjecturing and have decided to call it a truth. Like they just assume there was something that ate tyrannosauruses, and so they just make up some other organism. They don't need any bones or anything. It's just some sort of, there's just no distinction between what they've theoretically decided is true and what they have evidence demonstrating is true. And then, of course, the things that there are evidence for, the evidence is really crappy, and they don't point out how, yeah, but the evidence is really pretty crappy. They just declared a truth. It has been proven. Let's see, it's important to have a voice of rationality and dissent out there that isn't a carbon copy of predictable or mainstream dissent. I don't even know if there's such a thing as a mainstream dissent. So that's, again, just, I'm just being picky. I mean, I just happen to read it and say, oh yeah, wait, that doesn't make much sense. But clearly most of the dissenting community is really just a truther community. They're just scapegoaters. They hate something. It's like they're anti it, and that's it. They're just kind of like religious people, and they have a devotion, and they got a little horny for something, and that's completely biased to all perspective, and they're just as bad at doing science as the scientists they're critiquing. Your contributions to philosophy say enough people should be able to respect your opinions on physics. Well, I don't think anybody should be just given respect without earning it, but I would just argue that I think I have earned it, in the sense that I mean, even the Professor Lewin videos, I mean, I'm providing the conventional argument plenty of opportunity to make an argument and present their evidence. And I have clearly pointed out where the evidence is wanting and lacking and weak, and, and they should respect the quality, let's say, of the criticism. It's not just saying, Wilbur Winkadink thinks it's wrong, David D. Hilster says Einstein's wrong, therefore Einstein's wrong. I mean, I'm not doing something that simplistic. Whether or not they're perfectly worded or phrased, well, I think they're as well phrased as, again, conventional physics is always putting its foot in its mouth, right? I mean, 1 minute, well, this video I'll probably get into light and diffraction and interference and all that crap. And this fractal woman made a video, and then somebody's going to be asking a question about it in a sense. So they have these kind of contradictory statements. You can have interference without a cause, in the sense of you don't have to create the wave function. You don't have to have an obstacle to create a wave function. So somehow you don't really need the wave function. Somehow independent photons that aren't wavicles or haven't been converted into the wave function somehow can interfere. So it's like they're telling two different stories. It's called charity. Well, that's a dirty word, really. So yeah, in debate terms, and people should learn it. Yeah, I don't. It's already you've already kind of lost the cause if you have to use a word that has a taint to it, and certainly the word charity doesn't mean anything more, because that's just thieves and self-interest and a lot of things. People pretend to care about other people while they're making a living, selling them pills and shit. Lots of just too messy. But the word respect used earlier, you should respect first sincerity, and then courage. There's different things you should have respect for, and you can make a list of those things. And I certainly put an appearance of honesty anyway. You can never tell it's entirely how honest somebody's being, but I think any fair cop would say that I'm making every effort to be honest. All right, so Bob Thefty. Oh, the fly again. Yes, I gotta remember the fly. You should capitalize the F. A neutron weighs 1.56 electrons, more than a proton. Again, and how this weight is acquired through what process, right? So I just played the other day the video of how they measured the mass of the electron, and although some of the experiment is right there in your face and you can see it, some of it isn't. So to know the mass, you have to know the speed of the electrons. So if you have the speed number wrong, your mass number is going to be wrong. So you saying that they've done these things, I mean, electrons are hard enough to do, protons harder, neutrons have to be the most difficult thing. Because you can't they are a composite particle, and how are you going to account for all kinds of motion within the object? And it's just too difficult. I've done the calculations myself, yes, but it's not just all calculations. It has to be based on experimental data, and as the electron experiment demonstrates, the experiment's only going to give you a certain amount of information, and you're going to have to be able to, if you don't have any pre-knowledge of what parts of the experiment are doing and have accurate knowledge of that, like I said, how fast the electrons are moving. So they have a presumption about the speed of an electron with a voltage applied. Now, how did they measure that? I like the idea of the extrapolation of the Lesage gravity. So again, I just point out, I didn't know Lesage existed. Lesage is sort of a lie because it's really Fadio gravity. I don't know why. I mean, this is like the unfairness of the Young experiment getting touted as if it's some sort of, as if it meant anything at all, when it was a nothing experiment in the context that Newton had already done diffraction experiments. He had already found Newton's rings, which are the single slit pattern, and he had already done the single hair, which is a form of the double slit experiment. So why was Young remarkable? And I'd say the same thing. I mean, I don't want to fault Lesage because he did try to, I mean, he paid, to take all of Fadio's work after his death and do something with it and all that kind of crap. So, and he did the work of trying to sell it, try to sell the idea. So, but it was Fadio's idea. And again, it goes all the way back to Newton. But anyway, I didn't know any of those two characters when I came up with my theory. So I'm just saying I'm not really using that as a platform. Clearly, it's a rational idea because, like Fadio, I thought of it too. It makes sense. And the attempting to unify all forces into one force. But again, they sort of do that all on their own. They're sort of screaming, we're the same, by the fact that they go the same speed. That's just, you know, a huge indication that this is the same stuff. If you could get a complementary set of mathematics, so again, why do I need new math? I don't know why you think, because I'm saying their causes are wrong, I need new math. Their math isn't describing causes, it's describing effects. I just, you know, these people who think math is physics, it isn't. Physics is a movie, a description of motion. Mathematics doesn't even intuitively do that. I can tell you pi r squared or something. I could even say pi. And you have to draw a picture of it to really get it, right? Okay, diameter and circumference. I mean, they're images. Okay, they're not mathematical. So it's not 3.14. Do you think 3.14 automatically says the relationship between this distance and going all the way around the circumference of a circle? It doesn't say that. So why this horny for math? And again, why do you think, because I'm saying all their causes are wrong, it's push rather than pull, that somehow the effect itself is different? Because Einstein says it's bent geometry, and I say, no, it's just the inverse square law. Okay, you don't have to bend space to do the inverse square law. To do the inverse square law, you have to have pressure. That's all. An evenly distributed external pressure will create the inverse square law, all on its own. But nothing else necessary. Why do I change the math? The inverse square law is what we're both describing. He's describing it as being caused because space is bent, and I'm saying, no, there's just pressure. Pressure causes it. Pressure going to a point. A center of gravity causes it. To verify your model, it would be much harder to dispute. Okay, so I don't know. Should I just copy everybody's mathematics and put my own name on it? And somehow that'll make me right? So I'll just take all of Newton's formulas, I'll just put my name on them, and I'll take Maxwell's crap that's mostly right, some of it's stupid, but anyway, I'll put my name on it, and there, that'll make me credible. It's just, I don't know why you think, I don't know why anybody rational thinks this Rube Goldberg thing, this machine that is the universe, is somehow not drawable. That somehow I can't draw where the bowling pin falls over and hits the mouse trap and then flips the piece of cheese into the bucket of water, and the ripple in the water goes over the edge and the water hits the you know, whatever, nitrous oxide and blows up the tank. And I don't understand why do you think I can't draw that? That somehow you'd rather have mathematics explaining the trajectory of the cheese, and that somehow will make more sense to you than if I draw you a fucking picture. It's just, you know, it's all just geometry. It's all force and geometry and algebra. There's nothing here. There's motion and directions. That's what the universe is made out of, motion and directions. You draw a picture of it, and then you can just make it a relative drawing, like a matchbox car. You know, it can be like a little perfect representation of the original big thing. And you just made it small on a piece of paper. What's the big deal here? So anyway, it's just so annoying. Because really, I can't change the math. I can't make it not the inverse square law. Okay, that is, Newton is right. That's what it is. It's the inverse square law. That's the law. The new theory isn't going to change that. Conceptually, I prefer your model because it simplifies complex problems into intelligible ones. And somehow, though, you think the simple model needs more complex math, or some other kind of math. But whatever. I think that it would be interesting if you feel like it. Sit up straighter, my back's going to get worse. If you feel like it, to see a video. It'd be interesting, if you feel like it, to see a video of you critiquing the degree to which the results of an experiment are off. Well, again, most modern experiments you can't even analyze in that way because I don't have all the equipment. I mean, I don't have, you know, perfect vacuums and super lasers and all this other crap. So what's the point of trying to do any of that? I mean, so much of their experimentation is all black box magic stuff anyway. You know, oh yeah, we have this magic crystal that creates 2 instantaneous photons that happen to be entangled. I don't think I can do that on my porch. The plus and minus variance, R squared, data, etc. So again, I guess you have some doubts about the R squared as being a rational constant of many many elements of force are radial, and therefore the R squared fits because it's radial and fits the, you know, when you take a, you know, spherical. True point source. Thanks for the reading. I don't know what the reading was, but okay. Boy, you sure are one ugly mofo. Wow, I'm impressed. That's from Fib Not Now. That's important. Stole some chick image, you know, with her tongue after whatever. Licks some ass somewhere, no doubt. But what's the point of that? Jeez. You really think I have a vanity problem? Like somehow you can make me feel bad about how much, you know, better looking I am than most of you people? You really think I have that problem? You're pretty funny then. I mean, I'm, you know, just months from 60 years old. Doing okay, fuckface. No doubt doing better than you. So, what an asshole. Anyway. Alright, Lena Engineer is back. I haven't seen her in a while. Haven't been that kind, actually. I am curious if you can comment how holographic projectors work. Well, apparently holographic projectors, I don't think, are actually... So they're very strict about the use of the word hologram, because it is a specific kind of technology, and these other imaging mechanisms are not really true holograms, even though they're calling them holograms. And so this is a whole bunch of... But again, this gets into this subject. I've said it before. Optics. Huge, important subject. Lots of stuff going on. The whole thin film diffraction thing, the whole way beam splitters work, all that stuff is really important. But it's really, really complex. So you really have to watch, be very careful in having somebody tell you what's happening when they explain a cause or an effect. They use a word like diffraction, or they use a word like interference. And they really don't mean interference, you know. And it's just very dangerous. So I'll talk a little bit of hologram, I guess. Work in your model which depend on interference patterns. See, that's what you're saying. It's you know, clearly it would be an example of interference in kind of a bizarre way again, because the idea would be, I mean, the true hologram is created by splitting laser light, monochromatic light, and hopefully very coherent, you know, good phased light. Everything's in as much phase as possible. And you shine one beam on the object. So these are lasers that are spread. You spread the laser light, shine on an object. And you have another beam that you shine on the film that's looking at the object. Now there's no lenses involved. So there's no focusing, there's no, you know, so this image is not really an image as we know it that's going to be created. But you can sort of understand that there's two beams coming out of the beam splitter, this one and this one. And they're both going to be hitting this, you know, you hit it with a mirror to shine them both at the object. I mean at the photographic material. And again, there's, you know that when this light hits the object, that's supposed to collapse the wave function, right? When it hits the target, there's no more wave function, right? So how can it still have a wave function? And then these two beams somehow interfere with each other before they hit the photographic plate. That wouldn't really make any sense, does it? So this light's coming this way, and this light's coming this way, and somehow they interfere with each other and hit the photographic plate. Now, you can sort of get that this one can't possibly still have a wave function, can it? It hit a solid object. Now this one hit mirrors. That should collapse the wave function too, right? I mean, what's so magical about a mirror that it doesn't collapse the wave function? So, you know, what's the true story? Is the wave function a real thing or a fake thing? Can individual photons interfere with each other? Or does one photon split in two and interfere with each other? See, it just doesn't, there's no continuity here, no consistency. Alright, so I'll sort of explain. I'll explain what I can explain of the phenomenon. So one thing you should understand is a true hologram is really the creation of a diffraction gradient of sorts. It's a surface. Okay? So what you're really doing is creating dents in a surface. You know, dents in the surface. Because the hologram can be copied like a record. Okay, so it's a real impression made on the film. And so I'm just saying, that's something to understand. So anyway, so related to this, Fractal Woman is making one of her videos, and sorry, one of her videos, doing this kind of semantics crap of playing with their conventional physics has lots of kind of messy constants, and especially, like I said, the ones used to create a common amount of something. You know, so whether you know, and this is really bad when it comes to quantities of energy. You know, because you have lots of ways of expressing it: wattage, horsepower, kelvins, you know, all kinds of calories, different ways of saying the same thing. So they're very inconsistent constants. So in this case, she's playing with frequency and wavelength. Well, I don't see any point in playing with them. They obviously use them for two different purposes, but they're just inverses of each other. And that's all. So just, you know, the frequency equals the wavelength over 1, and the wavelength equals frequency over 1, kind of thing. They're just reciprocal numbers. As one goes up, the other goes down. So it doesn't mean anything. It's the same thing, just put in a different form, but it's saying the same thing. But the danger is that she's done this drawing that, you know, that is, you know, she thinks she's simplifying it because she got some arguments about, you know, you make a regular wave, you say, well, where's the photons in this wave? You know, where's the quanta? Does it start here? Does it start here? Is it this whole wave one photon? Is this, you know, what's the one photon? So then she takes what's traditionally one wave, which is both the up and down, and to satisfy somebody else, she converts it into two, which means now there's two photons. Because the one wave was supposed to represent one wavelength, so it would only be one quanta. And the real problem is that the quanta has to reach the node points. So this is the distance of 1 second heading towards the moon. And clearly the way she's drawn this, the quanta are here. So they haven't even reached this point. You can sort of see, I mean, it's a halfway point between them, but that's not that's not where the light actually is. So you have to count the nodes. And so in a sense, there would be 3 quanta in one wavelength by her description, when clearly if you did it by just looking at the dots, you'd say this distance to this node is one wavelength. That's the frequency. And then to this dot is another. So 2 wavelengths would be 3 quanta worth, because you have to count the nodes. You have to count the endpoints, have to be intact to get your distance right. You can't be at that distance unless you're counting that node, that 0 point, as the beginning or the end of the beam of light. You can't have it as a 0. It has to be a 1. It has to be on. It can't be off. the start of the ray of light can't be no light. There has to be a quanta at the beginning. So anyway, so this is where this just all gets kind of convoluted and confused. So clearly her fundamental point is kind of obvious, that in a certain, if you're measuring by time alone, then you can get rational numbers, because you can say, yeah, I didn't turn the beam on and off. So for a full second the beam was on, and here's an ultraviolet light and here's an infrared light. And then you can measure that the two beams have, there's twice as much energy in the ultraviolet light, because the waves are twice as close together. Therefore, there's twice as many quanta of energy. So it doesn't really have anything to do with being innately more energetic, beyond the fact that there's more cannonballs in the ultraviolet light than there is cannonballs in the infrared light. So that is perfectly sensible. But these drawings are not. So that's probably all I need to say about that. And we'll move on to, I'll draw something. All right, so holograms. All right, so yeah, so a lot of this I can't explain because I haven't done enough. I don't have enough information. I mean, I was watching, a few months ago, quite a lot of optics videos, and it just got a little bit too, it's a little too much information, so it takes time to absorb stuff. But what I did in the time being, a thing that was occurring to me in thinking about light, can't remember what exact circumstance it was, but I started thinking about eyes and apertures and what they do. Why is an aperture a lens? Okay, and this goes sort of to the whole distance size thing with the universe, and how photons get to us, and how objects that are really far away, they aren't really small. I mean, we see them as small, but they're still just as big as they were. They're still big things. We see the tiny dot, but they're still big. And you have to understand the light's still coming off of a thing bigger than we are. When you're looking at a star and you're just really looking at a galaxy or something, galaxy's a lot bigger than you. It still is. Even though it's far away, it's still a lot bigger than you. Alright, so size is really important. And so you could sort of think, like, if I was to take your retina and just make it into a flat plane, right? Because your brain compensates for the roundness, so let's just forget about that and just say this is a thing absorbing photons. And it has a bunch of little pixels on it, just like a computer screen in reverse. Instead of producing light, there's a bunch of little dots on your retina, and they're absorbing photons, saying on, off, on, off. Well, the trick is, without a lens, you have to understand that, okay, so what's going to happen is every point on this surface is going to send an image. And the trick is, it's going to send, every little point here is going to get hit by light from every single point on here. So every little pixel is going to get hit with a number of beams of light from all these different locations. So every location on your retina, every single little dot, is going to get hit by light from the entire image. And what it's also going to be doing, okay, is it's going to do the opposite, in the sense that one point on the image is going to hit every single bit of your retina. So one spot is going to hit every single spot on your retina. Alright, so in holographic imaging, you have to understand this is really what it's doing. It's seeing both things. It's collecting image data at every single pixel, and one set of data has this whole big image on that one pixel, and this other set of data has the whole image on this whole set of image collecting. And so that's quite confusing when you think about it. And so what's happening is when what we're doing, what our eye does, creates this little aperture, your eyeball. And, and so all of this data that's diverging, so this red stuff, that doesn't get in your eye. So all of this stuff that might be considered noise, that is from every pixel, all this red stuff is coming in, coming to the image. So all that stuff just isn't going to get to your retina because it didn't go through this little hole. So you're getting rid of all that red noise. And you're essentially collecting the image. Alright, so the only light you're going to collect is this little bit that comes into the hole here. And so it's going to be, the light that can do this and do this. And so all of that light is the light you collect. So then your light, the vision you're going to have is not going to be, it's not going to have all that noise in it because it's a much cleaner image of just the data coming from the individual locations to individual locations. So it's going to represent location data without having the single point sources creating all this noise. Now for the hologram, like I said, that's not what they're doing. All of this extra data is getting to the film. The film doesn't have a lens, doesn't have an aperture, so there's nothing to filter out all of that. And they say with true holograms, you could, with the finished product, you had a holographic image, you can cut it in half and say it had an image of a person or something. You can cut it in half and the two halves will have the whole person on them. Technically, so it's as if, the data is in some other form, clearly, that this whole image is somehow on all these little pieces. It's collectively stored everywhere. And so that's a whole different kind of thing than what we think of as regular images. So it's nothing like a regular image in that sense. And it's certainly not working anything like our eyes. So anyway, so that's something I've been thinking about just because of this distance thing. And as you get things move away from you, they can't really get smaller. They can't, because something's moving. The whole relativity argument. Well, which one's getting smaller? Am I getting smaller, or is it getting smaller? It's just a stupid question, a stupid point to make. And the light has to be traveling in straight lines, so what you're reducing is the number of angles from which you can collect the light. Well, in some respects, you're increasing them. See, if you were right next to a giant galaxy, obviously you wouldn't be getting too much light from way over here in the galaxy. So the further away the galaxy goes, the more light you're getting from the fringe areas, and the less you're getting from the center. But anyway, that gets a little complicated. So I don't know if there's any other point I directly wanted to make except for this. So another thing about holograms is that the thing you're imaging usually needs to be textured. It needs to be kind of lumpy. And so that sort of makes sense too, because what we're really doing is the beam that's being shown onto the film after the mirrors is like a reference beam. So this is really about phase again. And so the real point would be as the light, you're shining off the object, and then the film is like at this angle. It's a little complicated. You shine light onto this, it shines onto the film, this shines onto the film. So they're not perpendicular, or they're not parallel to each other. They're at this tangent angle. And so what you're doing, in a sense, the texture would sort of mean that you're changing the phase of the light as it hits an object. And so you have phase differences. And so that would mean if my photon theory is correct and they're actual corpuscles, you could understand that if light was coming from two different locations to a common location of an electron, that the out of phaseness, okay, of these two beams would mean that you could put a bigger or lesser dent in a surface. So if this thing hits and then this one hits and then this one hits, you know, if like this was 1 and then this ended up being 2 and this ended up being 3, that's like getting hit with a X-ray or something at that particular location. So this would create a bigger dent in the material, theoretically, than if it was at phase. So again, that just becomes so the reference beam is just really establishing a code for how deep these photons were hit. And so when you shine light back through the hologram, you're seeing the diffraction that's going to be a reflection of how deep this impressed the material in the first place. So how deep the valley is going to dictate you know, how much refraction there is or whatever in the light that comes out, deflection, and that will be a representation of this code, because without this reference beam, the out of phaseness of this beam wouldn't have meant anything. It still would have just been the same frequency light, and it couldn't have possibly created the extra deep valley. And it can only create the extra deep valley because of the out of phaseness. Something like that is what the mechanism is. So the interference essentially happens on the material. It doesn't happen. See, they're like implying. Let's see if I was to draw it. You know, this kind of idea. So let me turn the paper around. So the object's here. The film is here. Okay, the mirror's here. The beam splitter's here. So the beam splitter does this. All right, so you spread your laser light here. Your monochromatic light, I think, is all you really need, and then you're also spreading this beam. And the photographic film has to be this way, or you can't hit it. And their impression is that the two beams interfere here before they get to the film, when I think it's kind of obvious they're interfering when they hit the surface. And the interference is, I don't know how to say this, I mean, it's not really interference. It's either constructive or nothing. So you're really just talking about where did they constructively interfere, that is, create more energy, and where did they not create more energy. By being out of resonance. So again, we're back to this resonance argument. This is key to electrons and moving them. You have to hit them proportional to their pressure to be able to get them to go somewhere faster or further. It's not so much about how hard you hit them, it's how often you hit them when they're moving the right direction. So if you can hit them when they're moving away from you, you'll get more out of the energy you hit them with than if they're moving towards you. Yeah, that seems kind of obvious. I mean, obviously wrong word. That seems like something you can get, that's as an idea that's viable. And that's all I really need to do, in my opinion, to answer the question, number one. And it's a really complex subject. So, and again, so you read stuff and they'll use a word like interference, and you're just saying, no. Not the way you're saying it. Because again, they're not wave functions. And how do things that aren't wave functions interfere with each other? So they have to be, the interference has to be in a form of either constructive, in the sense that they're adding to the energy, or subtracting to the energy. You could also think about it in another way you could illustrate the mechanism, I suppose, is to think about it, you know, in terms of another phase argument, that the reference light hits the surface at a frequency, and See, it might just have something to do with the angles too. So I'm just thinking the two lights will be coming from two different angles. And so you're talking about two different kinds of momentum, creating a third momentum. So if the reference light isn't on, when the photon coming from the other direction isn't in phase, then the direction of the momentum of the electron will be this way. And if it's off phase, and there's when this one's on and there's nothing coming from here because it's here, right? So they don't match phase, then the reference just makes the electron move this way. So the only time you're really making the image, you could argue, is when the two are close enough together, hit at close enough phase, to create an impression in the material in this direction. So the holographic image is in this vector, and there's just noise here and noise here. So these directions don't have any value, and this is the value of the one you're getting back as your holographic image. And because of the slight phase differences from the distance around, say if you're taking a picture of me, the slight phase difference on each little surface of me, tiny little differences in the height of that reflection. So the distance between, you know, the atom right here and the atom right next to it, tiny little differences, and that creates a tiny little change in the phase, and that tiny change in the phase will create an image that's just a little bit off, a little bit more off, a little bit. So the more texture, the more variety you get in the impressions left in the material, and so therefore the more images technically that can be hidden inside of inside of just this. This is what you're really saying. You're saying here's the two noise signals, and all the good signals can be anywhere in here, and obviously as you move okay, from your location from here to here, you'll be seeing these images that were at different phase angles in their creation. So this is probably the better explanation. It's the one I just thought of, so compared to the other one, but it's the same idea. All you're talking really about is momentum, and I just never really thought about the two images coming in perpendicularly, and clearly, yeah, so if the photons are missing each other, you know, you can sort of get it, right? If they're out of phase, then essentially this photon will miss this photon. But if they're in phase when they hit the surface, then the net vector will be the vector. So the amount of phase difference between the two will dictate whether it's this, or whether it's this, or whether it's this, or whether it's this. So when they're perfectly in phase, they create an image dead 45 degrees. That kind of thing. Yeah. So it's something like that, in my opinion. So when you reshoot the light through at the same frequency to get your hologram back out, you're going to see these images because these have canceled. It's probably not, I didn't say that the right way, but these are the ones you're going to see because they're all going to be illuminated, and these are the ones that are going to have the image data in them. These are the ones that have the image data. These all went to the same, see, these all went to the same location, they're dead. These are all in different locations, so they have the different surface image data in them. Yeah, that's another way of saying it. These are like all 1 pixel. Everything's going to be that 1 pixel, that one location. And this is one location. And this is where you have a bunch of locations. So that's why you can store more than one image, essentially, because it's got lots of locations for those images. Where if the light just went this way, that's a dead pixel. It's going to be used over and over again, where this won't be used over and over again. Probably something like that. So anyway, I think I've done what I wanted to do, which was just provide some reason for you to understand that because they say it's interference doesn't mean it is interference, and certainly doesn't mean it is interference in a classic two-slit experiment kind of bullshit way. And it's just unfortunate that I think this is what's really wrong with physics, is that they just do way too much of this stuff. They use these terms that aren't applicable
since I'm calling this
in all these circumstances.
So
it's just wrong. Wrong answer. So anyway, I think that's enough now. Yeah, this image is all cut off. I have to put it in a different location. No, I have to just move this up. That's what I have to do. Alright, anyway, it's a problem for some other day. So, till the next time and such, I think that's all I had. See if there's anything new while I'm here, but I doubt it. Oh yeah, then this image is going to get my way now. Too many things to manipulate. And nothing there. And try the comments. Well, I should just hit F5, right? That'll work, hopefully. I think it worked. Yeah, it worked. Okay, so till the next time and such, so forth and whatnot. What am I trying to do? Oh.